Hi everyone. I like to introduce Chris Vogt. He has worked many years with Scala, Python, and PHP. He's a former member of Martin Scala development team and open source contributor to a number of libraries for the past few years. Chris has been working with Haskell in the enterprise blockchain space and Symbiotia.io. Today, his work goes through software like Lego, how Haskell naturally delivers on a decades old dream. Over to you, Chris.
Thank you for the introduction. Right. Okay. So let's talk about how Haskell can be a little bit like Lego. And in a way, that's software engineering's old dream, isn't it? Like assembling software from pieces like Lego. Kind of what they thought about in the 90s with, or before, with the architecture, and it's kind of what we always hoped, right? So how is Haskell like that? Well, to me, at least, it often feels like Lego or just putting puzzle pieces together, right? And like the kind of the takeaways I hope you get from this talk is maybe a little bit of food for thought, maybe a little bit of more understanding of how Haskell enables composable code, also where maybe complexity in Haskell code arises, and where Haskell could possibly provide better composability. Maybe a few new observations, or at least what tabs and blanks are. So let's compare Haskell to Lego or puzzles. And well, Lego is creative, it's fun, it's putting simple parts together, it's building something sophisticated. That's all things that I associate with software development. And well, jigsaw puzzles, it's kind of like you choose a picture and then you put the pieces together, right? Isn't this like choosing a signature and then Googling the pieces that kind of make it work? And well, when I submitted the talk, I thought about Lego because of all the positive associations, but I feel like at the end of the day, the jigsaw puzzle comparison works a little bit better for what I'm trying to do. So we'll roll with that. And let's start with jigsaw terminology. So these holes there, they're often called blanks. And these knobs, they're called tabs. And I'm going to kind of use these terms as they come up. Maybe I'll say knob instead of tab because tab is kind of confusing for programmers, but just to know what I refer to when I say them. And let's look at a puzzle piece that has one blank and has one tab, right? So what kind of Haskell stuff looks like this? Well, a function, right? So toUpper takes something, produces something else. So it takes a text, has a blank text, and then it has a knob, a tab text. Makes sense. So more generally, functions like a puzzle piece or a function can basically be thought of as a puzzle piece that has a hole that you need to fill in and provide something that something else can consume. And one thing important to note is that obviously, kind of sticking with the analogy in a way, the knobs of the puzzle pieces would have a different shape for each different type, right? I didn't want to draw a ton of puzzle pieces, so I'm using the same shape everywhere. Just imagine it had a different shape for every different type. So obviously that only puzzle pieces that have the same, like provide and consume the same type fit together and others do not. And let's look at putting two puzzle pieces together. So I guess one thing we noticed already is, okay, we're composing two lower and length. Well, I guess that example doesn't make super much sense because two lower doesn't really change the length, but let's roll with it. And well, I guess I thought the puzzle pieces from left to right, but then we compose right to left. So let's actually flip the puzzle pieces around. There we go. Yeah, but I mean, function composition, kind of easy, right? It's like plugging two puzzle pieces together that have the fitting edges. Really building a chain of functions that we compose feels a little bit like putting pieces together. In a way, this is like Haskell makes this particularly easy and nice. In many other languages, more looks like this. So the syntax doesn't really compose. You have to kind of put something in the beginning and the end and nest it, and it gets very hard to see. And then maybe you have to kind of pull some things out to make it more readable. So like the lightweightness of Haskell's function composition syntax really encourages this kind of plugging stuff into each other way of thinking about code. So yeah, and I feel like one of my takeaways, or one of my almost surprises when I started writing Haskell on a daily basis, was that syntax matters more than I thought. I feel like way back as a junior developer, like we all obsess about syntax, and then we realize more and more like syntax matters a lot less than we thought, and semantics are actually more important. But then at some point you start realizing, okay, in some places syntax does actually matter, and having the right syntax does encourage also doing the right thing. I feel like this is really one of the lessons I had writing Haskell, that the syntax does actually support doing the right thing many times. Okay, let's look at other puzzle pieces. What would that be? It's something that provides a value. So it's just a value, right? Let's say foo is a string, and well, it's of type text. So any self-standing value would be a puzzle piece that we can put into a hole. So we can plug foo into toUpper, right? Or Haskell does actually also provide a way to kind of flip the puzzle around and do it that way. I don't know if you know that this ampersand operator, but I think probably most of the time it's not. It's like better to just use regular function application. But in some cases where the value you're passing is small, but the function call is large, like you have a lambda case or something, it's kind of nice to have this choice of writing it this way. Okay, one more puzzle piece. So I guess this is like an end. This sort of terminates the puzzle, right? So what kind of Haskell code would be like that? Well, I guess first thing comes to mind is A, like any type A, to unit, right? But that's not very useful. That just makes the value disappear. So I guess something more useful would be something that does something with the value, even though it doesn't really produce something. So put strlen, for example, takes a text, doesn't produce anything. And so this type of puzzle piece would be a function that goes from a value to an IO of unit. I mean, it makes sense. The main function is of type IO of unit. It basically consumes what the program does and then terminates the logical flow. Okay, so we can put this together. We have a very simple puzzle that's nice for starters. So in a way, these parts, they kind of felt like puzzling, right? Like, or well, they felt like putting a puzzle together. Hopefully not so puzzling. Let's look at a minor thing where I guess Haskell syntax is a little bit at odds with this puzzle comparison. So in the lower part of this slide, we see three puzzle pieces put together, right? Put strlen to lower to upper, function composition with the dots. But then in the top, when you want to plug the last puzzle piece in, which provides the value, the dot doesn't work anymore. So in a way, like I like to call it, like the composition syntax isn't stable. So suddenly you have to provide this $sign or parentheses or something to distinguish it. I mean, there's a different way to write it, which would be like this, where it is stable. You just add $sign and the value, but then most of the time you wouldn't write it this way with the additional symbol, right? So, okay, like in reality, this is something that when I rewrite code or when I change code, it is something I stumble over every now and then. Okay, I have to swap the symbols, la la. It's a little bit, it's like it's a small hiccup, but still it's a hiccup. So yeah, observation is like Haskell syntax works for thinking about code as like composing these puzzle pieces together, but it's not perfect. But then nothing's perfect, and often there's some kind of trade-off involved, and yeah, with syntax as well. Even though I don't know what the maybe there's a different type of syntax you could choose that might be more supportive of this puzzle-like thinking. Okay, Here's another puzzle piece. I guess it's a bit unusual for jigsaw puzzles to have like the openings, the holes on the same side. But yeah, what would that be? Well, how about this one? A function that takes 2 arguments. Intercalate takes a separator and a list of strings that should be joined with a separator. So it has 2 arguments, produces a new one, produces a new value. Okay. So more generally, functions from multiple arguments to a single value. Or more generally, like any kind of product type in a way supports this notion of like, oh, plugging multiple things together into one thing, right? Nested tuples, or well, tuples in general, records. You take multiple things, you make it one thing, and then you can plug this one thing somewhere. And yeah, let's talk about currying. So now we have functions with multiple arguments, right? One thing that I also found a little bit surprising, just using Haskell, I mean, you get the notion of currying before, makes sense also because of how the Lambda calculus works, and makes sense as an implementation technique, but it wasn't obvious to me before I started using currying how well it actually works for as a user interface, like the experience. And let's look at an example. So we can already see that comparing to jigsaw puzzles doesn't scale all the way, right? Now it gets go. With jigsaw puzzles, obviously, we don't have new pieces that are built out of other pieces, which we do here. But I mean, down there we have a chain of calls. We produce this list, then we take the first 10 elements and we map over the elements. The expression isn't super sensitive, but let's roll with it as an example. And then the take 10 obviously is the right puzzle piece, and the map is the left puzzle piece. And then those are, like, since these functions take 2 arguments, we kind of fill in one of the arguments already. And then what remains is basically a linear puzzle piece. And I feel like this is really one thing that makes currying so useful, that Haskell in general, but also currying kind of encourages you to have like linear snippets in your programs. And things being linear is easier than things branching. It's following a linear flow is simpler than trying to figure out what some branch logic does in your head, right? So yeah, it's kind of it supports this ease of just plugging things into each other. Loops, well, I mean, sometimes we write recursion by hand, but in many cases we just use the existing things like map filter, or even unfold or iterate, or those, and those plug like puzzle pieces. And here's also something that's kind of interesting, where, well, function languages also support you in this like plug stuff into each other experience. And that's this notion of you can easily transfer basically control flow between functions or between puzzle pieces. And the technique here is you would do it through the type. So the thing, yeah, the knob, the type of the knob basically is what transfers the control flow. And yeah, obviously this would be through some types, right? Like an ADT. That let's say in this case has constructors ABC, and then you have some kind of case distinction that yeah, makes the different branches result in the different constructors, and then just pass the expression or the value over, and then the other puzzle piece can pick up where the first one left off. And somehow some types are like this type that a lot of other languages forgot, including like serialization libraries and all this. And it's just so useful to transfer control flow, right? And I mean, we have named ADTs, and then if you don't want to name an ADT and create a specific one, you can just nest ethers, even though it gets a little tricky if you have a left of a left of a left. Then union types, I guess, would be the anonymous way to do it, which Haskell doesn't have. Scala 3 has them, for example, but I guess they're becoming more available in functional languages. another thing that or supports this whole like feeling of plugging stuff, like assembling programs from pieces. And this is like a larger observation, not specific to the last point, more like, why does this entire, why does everything that we looked at so far even work? It's really because, well, because of types and purity and this enabling referential transparency. So we separate pure code, right, from IO or from effects. And really the pure code is what feels like things you plug into each other, because it declares everything that happens in its types, while in the effects that it's not all in the types. And that's why we separate, and we have as much as we can in this very, yeah, kind of pluggable style. But we'll get back to kind of IO and monads and stuff in general later. Here's another puzzle piece we didn't have yet. Takes one thing, produces multiple things. So what would that be? I mean, I guess you could think of a function that returns a tuple, but then a tuple is still one thing. And something else needs to sort of pull it apart in order to produce multiple things out of it. So that doesn't work. The closest you get would be a let binding, where you have multiple values that somehow are based on the same value, right? So you take one thing and you produce multiple things out of it. But unfortunately, this is really also where our puzzle comparison breaks down, because this doesn't really plug into something else. There's no clear line. Like anything in the expression below can use the things from this binding. There may be more bindings, and it's not like one clearly just separated piece that plugs into one other separated piece. It's more like a graph of interconnections of data depending on other data. And that also shows okay, this is here, it gets more complicated than just plugging things into each other. Or let me make this example or this point differently. Imagine you give this to your kid, right? Jigsaw puzzle. How do you know if she's a Haskell programmer? Well, if she gives you back this, she's not a Haskell programmer. Ignore the missing piece, but if she puts it nicely together, not a Haskell programmer. How do you know if she is a Haskell programmer? Well, if you get back this, bunch of let assignments, bunch of references. I mean, obviously this is a joke, but sometimes when you look at a code base that you don't know, it sort of feels like this. You're following references, you go there, and then a few references down, you're like, wait, what's the whole thing put together actually? What did I see 4 jumps, before 4 indirections? What did I see? Or yeah. So references can be a problem, like kind of naming things and referring to this later and having an indirection in there. This is obviously easier, right? But we need obviously bindings and references. There are many reasons. We sometimes want to just give something a name to document, or we want to reuse the same value multiple times. Or you have some complicated expression that you want to decompose so that you can make the pieces more easy to consume one after the other. Even though then in your head you have to rebuild what it basically means. Or without naming things and referring to them, how would we even decompose things into multiple files and export things and refer to them somewhere, import them somewhere else? We need somehow something to refer to those things, right? And reuse them. So names are incredibly important, and referring to those names, but there is a cost to it. And I guess with our comparison to the puzzle, we recognize that there's a higher cost compared to the other things we looked at so far, because it doesn't really work with this simple analogy. But generally the kind of cost is like name lookup. So you need to kind of go where a name is defined, sometimes in a different file. And then you have to kind of build this coherent picture in your head, which we saw was hard with the baby puzzle. And then also every time you define a name, in a way, you're branching, you're potentially branching your data. Multiple things in the block, or, well, if it's static data and you import it, multiple things can kind of refer to the same name, right? So if it's in a block, it's a local bind. You kind of need to read the whole block in order to understand how the data dependencies are and that they might be branched. I guess that's an artifact of how name binding works. You could imagine in principle having kind of a language feature that allows you to define names that can only be used once. But yeah, names do introduce complexity in a way, the way it's right now. So it's a trade-off, really. It's like names have cost, and cost and necessity are a trade-off, and names are incredibly important, but they're not always the right thing, right? So you have to kind of really choose where to use them because you build these graphs. And in a way, that's, I think, one of the reasons why some people prefer point-free style, because it tends to be linear, and linear is easier to think about than some graph. So let's talk about nested data. Before we had, we applied to upper to a value. So there the analogy with puzzle pieces works very well. But sometimes we have something that's more complicated, like a tuple or an either or something. Well, when it just comes to product types, I mean, there's Bifunctor for like first and second for either, but then there's lenses as well, which obviously scales to all the different product or sum types. And fine, so I guess you can take a tuple and just plug a puzzle piece into just one of the components, or just one of the sides of an either. So that's fine. I guess still feels like putting puzzle pieces together. Here we do the bifunctor, where we apply the function to upper to the first component of the tuple by calling first. But it gets a bit more tricky when it comes to like containers or functors or monads, and like things are nested there. And let's look at some stuff. So basic functor, fine. We can fmap over a list, for example, and apply to upper to every element, or use the infix operator. If it's kind of doubly nested, right, now it gets already like if you don't use this operator below, which I think is only in Protolud or some not super common library. Yeah, if you don't use the smaller dollar greater operator, but you use fmaps, now okay, you actually, it's definitely not linear. It's kind of gets a little bit more noisy, right? And if you go 3 levels, it's even worse. So definitely kind of, it feels a little bit less like putting puzzle pieces together because of the nesting. And let's look at another thing. So when monads get involved, let's look at 2 functions, f and g. F takes an a and produces something like a value b, but that's within a monad m. And g takes the same b, but produces the value c that's also in the monad m. Obviously, you can't do g.f, right? You can't just compose the functions, because that would expect, well, f returns m of mb, but g doesn't take mb, it only takes b. But well, there's the Kleisli, this Kleisli operator, which allows us to do this. So in a way, even in the context of monads, like we still get this puzzle-like program composition. So that's really nice. And let's look at another example for either. So let's say E is an IO of either AB, and F is a function that takes an A, which is the left side of the either, and maps it to a C. But also has an IO effect. And so we can't use, for example, the monad transformer except T here, because the monad for either is defined over either A, with B being the value inside the monad, right? So if you kind of treat either as a monad, and with a transformer you would do that, you can only manipulate B, you can't manipulate A. So that doesn't work. However, there is this function bind left in some library, which allows you to do just what we need here. It allows you to basically map the left side of this either into a value where the mapping produces an effect as well, and pull this effect out. So there are functions in the Haskell libraries that basically allow us to think about, to easily compose programs even in the light of effects. But then there are gaps too, right? So let's imagine IO of a 4-tuple, and now you want to map the second element to something with IO. And in a way, there are a lot of these operators, and you find a lot of them through Google. But it does feel like they're spread over a ton of different libraries, and the naming is sort of inconsistent, and there's pieces missing where occasionally you need to write something pretty tricky by hand. So I don't know, maybe we do need a new library that somehow consistently provides it for all the cases of like monads, nested with product types, nested with sum types, and make this easier. Because I feel like there are gaps. So kind of the puzzling experience, the puzzle piece to composition experience kind of breaks down when monads are involved, which is a little sad, and it doesn't seem like it needs to. Well, it doesn't always break down, but in some cases it breaks down. Okay, let's go full circle. So we're closing the loop. So back to software engineering stream, composing programs from simple pieces. I mean, much of Haskell feels like you're doing this sort of composition, right? I mean, there's room for improvement, but it does feel like just putting pieces together and it just works. But then wasn't the stream in the 90s about like interfaces and modules and making them swappable and putting together these complex structures? Yeah, but maybe that was the wrong dream, or maybe that was partially the wrong dream. So turns out this composition works really well when you do it at the level of like functions, individual functions, right? There are all these like, it's beautiful how all these things really fit together. And most of the I mean, it depends on your domain, obviously, but most of the code you write and most of your programs just need this. They don't need these swappable parts. They can be built from just functions that compose really well. But I mean, we do need both. We also need modules. We also need kind of swappable interfaces. Just, I feel like maybe one difference between kind of the object-oriented world and the functional programming world is kind of the object-oriented world made it kind of, they thought like, okay, modules and interfaces are really important. So this is like, we make this a first-class thing. It's like super like, this is the thing to concentrate on first. And so it became so important, and it becomes such a thing that people tend to kind of use it too quickly or use it for problems where it's not necessary. And in a way, FP went the other way. It's like, okay, we'll do functions, we compose functions, like just loose self-standing functions. And sometimes even didn't have a great answer for the whole modularity thing. Like some people aren't super happy with how it works in Haskell, even though I feel like MTL, but also kind of composing records of functions works fairly well. Maybe because you're so explicit about monads and effects, it's a bit more clunky than just doing like composing stateful objects. But well, you get the safety, and the clunkiness doesn't matter so much if you don't need to do it everywhere, right? Right. So we need both. We need composing functions, and we need composing modules, which is a lot more tricky. But in a way, priorities matter, and being able to compose functions really well scales to a lot of the code you write. Right, and that's kind of the story I wanted to tell. I hope it was I hope it was interesting. I like this kind of picture of thinking about code as like putting pieces together, and was intrigued by how natural and easy it kind of felt writing Haskell code, and in a way how I always wanted it to be, but it never was like it. But it now it mostly is, and that's really nice. And yeah, I work for Symbiont. We hire Haskell developers. It's a great place. I've been happy here for 4 years. So if you're looking for something interesting to do, reach out. We're in the blockchain space, do some programming language development, and yeah, do a lot of distributed system stuff and these kind of things. Jama Lambda. I guess that is more of a comment. I'll read this later, but then CD Smith asks, have you seen code.world/blocks, which provides a very puzzle-like interface for composing functions as in your talk and generates Haskell? No, I haven't seen it. I mean, I've seen the interface for the Lego Mindstorms robots, and I think it's not specific to their system. It's a more general thing. I forget what it's called, but it also looks like puzzle pieces. Scratch, I think, right? The language, it's a visual language called Scratch, correct? And then there is Nomeata, which shamelessly plugs incredible.pm, a jigsaw-like UI. So the thing is, I think actually turning this jigsaw, I guess, comparison or analogy into an actual visual jigsaw-like interface, it is nice for learning. But as we saw already in the talk, the analogy, or the like, it breaks down in some places that are also quite important, right? So and also visual, like text is a nice medium to edit. So in a way, I mean, they try to popularize all these graphical languages, I guess in the 90s or maybe 80s or something, and the thing is, like, I feel like they did stick, just not in the software development community. So in game development and in business intelligence and in a bunch of different domains, like with like Unreal Engine or there's graphical stuff. I'm no expert at all. Or in the Tableau business intelligence software, there's a very graphical processing kind of I think it's called Tableau Prep, which is, it's basically kind of like functional programming. But just the graphical nature of it, I guess, for software developers makes it a little bit clunky to work with. So to some degree, I like it for everyday work. I like it more as an analogy, or as a mental model, where basically if the textual syntax of the language lends itself to writing code that is similar in this way, but kind of offers more power and flexibility, then it works really well in my. Well, I mean, maybe someday we'll get to more visual programming, but it hasn't happened yet for the software engineering community, right? Yeah. So yeah, VFX apparently is a visual effects software that is also uses graphical programming. And yeah, I feel like, I mean, it's both. Like, actually making it graphical is both great for teaching, but it's also really makes it more accessible to more people. In some way, like, it's something that the world is struggling with a little bit, right? That there's so much demand for software development and so few developers in a way. So it's kind of very abstract. I mean, if you want to be a software developer, first you have to kind of learn all the Linux legacy crap and all that. So unless you're in a very specific domain, but then it's, yeah, I guess that what's hard about it is that textual code is abstract and it does require you, especially when it comes to names and references, to assemble a lot of stuff in your head.